Okay, hey physics kids, it's Mr. Bryant again with the second of his video lectures on momentum. The topic we're going to be talking about are elastic collisions. If you recall, what we talked about in the previous lecture were inelastic collisions, where two objects run into each other and then move away with a common velocity. In those collisions, you conserve momentum in the system, but you don't conserve kinetic energy. In elastic collisions, both momentum and kinetic energy are conserved. What this means from a practical standpoint is that during an elastic collision, the two objects move apart and retain their own identities, their own velocities, and their own momentums. Think about what happens when two pool balls run into each other on a pool table. After they hit each other, they both move in their own separate directions. In an elastic collision, since each object has its own separate momentum and velocity, the total momentum before the system is equal to the total momentum possessed by two completely separate objects after the collision. So that's basically what the formula on the bottom of the screen right now is telling you. However much momentum you had possessed by the two objects before the collision must be the same after the collision. In addition, since no kinetic energy is lost, the kinetic energy of each object combined before the collision is the same after the collision. You should read the formula as following for each individual object. 1/2 times its mass times the square of its velocity plus the same value for the other object, 1/2 times its mass times its velocity squared, must be the same before and after the collision. In other words, as we see here at the bottom of the screen, the total kinetic energy of the system is conserved, just like momentum is conserved during an elastic collision. Elastic collisions are one of those things that in reality really don't exist. When two objects run into each other, we always lose a little bit of energy. If you've ever played pool or even ever just dribbled a basketball off the ground, think about what happens. When the two objects run into each other, you can definitely hear what's going on. When two pool balls will clack together, you can hear the bouncing of the basketball off the floor. That sound that you hear is energy lost from the objects turned into air vibrations as a result of the objects colliding with each other. So there's always a little bit of energy given off by the objects that's lost. There are some collisions, however, that are pretty close to actually being perfectly elastic where no energy is lost. So the formulas we have work in those instances, although they're not perfect. But since this is just a high school physics class, they work well enough for our purposes. Here are some practice problems for you to look at. Go ahead and try to give these problems a try. Get the answer. Then go ahead and move on and see if your answers are correct. At this point, I would suggest pausing the video, working the problems, and then moving ahead when you're ready. In the problem involving the collision between the moth and the jelly bean, I ask you for the momentum of the jelly bean after the collision. Excuse me, that would be the momentum of the moth. My apologies. To find its momentum, all you have to do is isolate m2v2 f, which is the final momentum of the moth after the collision. After manipulating the equation, we find out that it's 2.4 kilogram meter seconds. Notice how its momentum has gone from negative to positive. This is because the collision with the jelly bean has caused the moth to move in the opposite direction. The kinetic energy of the jelly bean can be found simply by entering its mass and its final velocity in the formula for kinetic energy. Answer here is 0.56 joules. In some collisions, the collision comes from the objects running into each other when they both start at rest. In these cases, the initial momentum of the objects is considered to be 0 kilogram meter seconds. The situations where these types of things occur, situations like a bullet being fired out of a gun, or two people on roller skates pushing away from each other. In these cases, the initial momentum of the entire system is 0. Both objects start at rest. After the collision, the momentum of the system still has to be 0 because we can't gain any momentum as a result of the collision. However, what we have after the collision occurs are two objects that each have their own individual momentum that's going to be some number other than 0. So we already have the answer to the question that you see on the left-hand side of the screen. What is the total momentum of the system after the cannonball that you see in the graphic fires the cannonball to the right? Excuse me, the cannon fires the cannonball to the right. Cannonballs don't fire themselves. At least I hope they don't. It'd be a much more dangerous world. The correct answer is, of course, is that the total system still has a momentum of 0. The forward momentum of the cannonball must mathematically cancel out the momentum of the cannon. In other words, if I add the momentum of the cannonball to the momentum of the cannon after the collision, it has to be 0. Here's another problem for you. We have two skaters, Marek and Nadia. I got these names, by the way, from people I knew when I were in college. They were interesting to say the least, and both of whom were skaters as well. So imagine they both start at rest. I give you the mass of one of them and their velocity after they have their elastic collision. In reality, the collision is just the two of them pushing away from each other, but the math still works for this situation. Can you calculate what Nadia's velocity would have to be after the push? Go ahead and work the problem, then come back to the answer. Since both skaters are starting from rest, again, the initial momentum of the system must be 0. Then simply enter the values for the known skater in terms of their velocity and mass. Isolate the variable associated with the final velocity of Nadia on the right-hand side and divide in the last step. Notice the sign of the answer here, negative 8.3 meters per second, is opposite that of the other skater in this case. Again, we should expect this because the two objects are headed in completely opposite directions. Since momentum is a vector quantity, the only way to properly represent the fact that the two objects are headed in opposite directions is to give them opposite signs, which in this case has worked out.